Now that I changed their names, they should be down here. Let's say delete assignment. So I deleted that one. I deleted that one. So at least it took care of this one class. I got a lot bigger problems with the other ones. But now just for the record, I was telling you I'd changed the dates. So what I have now for you guys, and this will be on recording so they so anybody else can hear it later. I will cut out some of the earlier stuff, but not this because I'm actually talking about stuff that'll help us. Good gosh, there's a bunch of students coming in. Angry. Okay. So just so you'll know, chapter 21, conceptual and homework are both due at 11:59 p.m. on 1/25. So that's like, I think that's, I want to say that's Tuesday night, but the main thing is January 25th. I've moved back the physics primer and the intro to January 23rd in case anybody hadn't done that. Again, 11:59 on January 23rd. And then chapter 25, I've moved back to 1/25 at 11:59, and the same thing with chapter 22 conceptual. So basically everything's due on 1/25. Chapter 23 would be the next one we cover. I haven't decided what I'm doing with that, but currently it's set at on January 30th. So that seems reasonable still, so I'll leave it for right now, but that might change later. So just as a recap, after I let all these additional people in, I'm going to say it one more time. Currently what I have is chapter 21 for this class is now, both of them are due at 11:59 p.m. on 1/25. I did move the physics primer and the intro to mastering back to 1/23. That's January 23rd. And conceptual and homework for chapter 22 are also due on 1/25. That should give you ample time. Let me see what day of the week 1/25 is, so just to make sure. So I usually don't do it like this. Ooh, it's not giving me my normal. Oh, there it is. Let's see, 1/25. What day of the week is that? Because I might want to move 120 chapter 22 back a little bit. Yeah, so that's you guys meeting on Thursday. That's right. So it's Wednesday night is 1/25. So yeah, I think that gives you ample time for chapter 22 and chapter 21, because chapter 21 should be done by now, at least by Friday to Sunday at the latest. So I think that's reasonable. And the chapter 22 is so short, that's definitely reasonable. So everything 21, 22, conceptual and homework are due on January 25th, 11:59, and the primers are due on 1/23 at 11:59, and 23 is the Monday night. So hopefully that will help everybody. And I did get rid of the extra two primer / intro to my lab and mastering. So we're good there too. It is now 2 minutes after class. So if anybody has any questions, now's a good time to ask. Anybody have any questions regarding text material, either from chapter 21 or from chapter 22?
Professor Younger, I have a question.
Yes.
These recorded lectures, where do you post them?
They're right here. I'm typing it in the comments.
Okay, thank you.
No problem. So that's my YouTube channel, and you can find them there. Just quickly, let me share my, well, let me see if I can even open it first and then share my screen. That might be a little more helpful. So, okay, now I can share my screen. So let me share a screen with you for a second. So this is my YouTube channel right here. And you'll see, for instance, what we covered is right here. And what we covered is right here. This is, of course, I covered 2 classes yesterday because I've got COVID. I had the, well, I'll say yesterday and the day before, I had COVID. So my face-to-face class had to meet online, and that's what this one's probably from. And this is probably from your class, as you can tell right here. Then I see that let's pause this. Do you see right here in the comments section or in the explanation section, it says PHY 242N05B, and notice that's the date. So if you ever go to my channel and you want to look for a particular video from a particular class, then you can just do search for 242. and that'll bring up your class. It'll bring up your class for every time I've ever taught it, though, not just your time. If you decide to type in just the date, that'll probably bring in your class and any other day I taught on that. But you see how I listed the date 01/17/2023. Not only that, when you go into my Google Docs, this will be the name of the actual Google Docs. This document that you see right here, that will be the name of it, so you can find it. Does that help?
Yeah, that does. Thank you.
No problem. If you subscribe, you'll and you can unsubscribe later, like I said, if you don't want that. But basically, if you subscribe, you can turn notifications on. I think it automatically has notifications on, period. But if you get aggravated with it, then you can turn notifications off. But as long as you have the notifications on with subscribing, every time I post a new video, it'll let you know. So obviously that's a wonderful thing during class, but you know, when you're finished with my class, you might want to at least stop the notifications from coming. Unless you're just a fan of my physics. It's without a doubt the sexiest, most cool website on the internet, and I'm sure I'm going to make millions and millions of dollars on it. So anybody else have any questions? All right. So last time we were talking about Gauss's law, and it started looking kind of confusing to you guys, I know. But I want you to step back a second and think of the process that I went through. If you were to look at the notes, which we can sort of look at, let's do that share screen thing again, because it actually shows some notes right there. Let's move that ahead. So what I was doing here was calculating the electric flux. And you can see from that document right there that I had drawn basically a little point charge Q at the origin. I then drew a sphere whose center is also the origin. And that's a sphere that I'm going to call later a Gaussian sphere. And what I was doing here was kind of motivating Gauss's law. In other words, I told you Gauss's law was about flux, and I told you the definition of flux is that flux, at least electric flux, would be the integral of the electric field dotted with the differential area element. And specifically with Gauss's law, we only use closed surfaces. So a toilet paper roll, you know, the little cardboard roll inside of toilet paper, that would not be acceptable for Gauss's law because it's got holes in the end caps. Whereas a soup can would be acceptable until it's been opened because it's got a cap, and then the label. That's a closed surface. You can integrate on it, meaning on the soup label and the lid and the bottom. You can integrate on that, and the reason being it's got a clear inside and an outside. So, for instance, you know, if you have, for instance, chicken and noodle soup in a soup can, you know, no chicken's going to get out of the soup can, assuming that really is chicken. But no chicken's going to get out of the soup can without passing through the actual wall of the soup can. That's what defines an object as truly closed. Okay, so that's what Gauss's law is ultimately going to do. I here happen to have chosen a closed surface, a sphere, and I'm doing what's called a surface integral to calculate the flux through that sphere. And I chose that sphere for a very good reason. What I know about that sphere is that a sphere like this has a vector, what we call a normal vector, to its surface everywhere that is in fact radial. So if I go right here on this part of the sphere, the surface vector is there. If I go to this part, it's there. If I go to the left side, it's pointing that way. If I go to the right side, it's pointing that way. If I go to the bottom, it's pointing that way. If I go to the front, it's pointing towards you. So the electric or the dA vector, which is always normal to the little differential area element on the surface, that dA vector always points along a line from the center of the sphere out to where you're drawing that sphere. Therefore, it's radially outward. Well, that's nice because the electric field, specifically from a point charge at the center of the sphere, also points radially outward. And that means that a dot product of E and dA is just going to be pure multiplication because there's no angle between them, or the angle between them is zero. So you get the magnitude of E times the magnitude of dA times the cosine of 0, which is just 1. And that's going to be the trick with Gauss's law. Even though I'm motivating Gauss's law right now, I'm not actually applying it. I'm using a way to justify to you what Gauss's law is going to be equal to on the right-hand side. But that's still going to be the trick to Gauss's law, is you always want to choose a Gaussian surface that is everywhere on the surface. Either the electric field is a constant, which also means that the electric field is perpendicular to the surface everywhere, or in anywhere that the electric field is not constant on it and therefore not perpendicular to it, then in those places, the electric field should be parallel to the surface or 0 or something like that. Because if it's parallel to the surface, and I mean surface, not the surface vector, then the dot dA will always give you 0. That means, it doesn't mean Gauss's law is not valid if that's not true. It just means that Gauss's law is not helpful in the way we're trying to use it if that's not the case. Because what we do with Gauss's law is we actually try to use it to solve for the integrand on the left-hand side of the equation. So if I fast forward this a little bit, you'll see ultimately, once this loads up, that's Gauss's law. Gauss's law says the closed integral, so that little circle on the integral just says, hey, this is a surface integral. We know it's a surface integral because it's got dot dA, and A is the surface area, or dA is the surface area. And we know it's over a closed surface because it has a closed circle on top of it. Later, we'll do line integrals. And if it has a circle over it, that means it's only a line integral along a closed line, a closed path. In other words, like a shoestring that you tie its ends together, that would be a closed path. Whereas a shoestring without the two ends, glued together or whatever, is not a closed path. So after that, it's just a matter of, can we find the right symmetry? And to be honest with you, there really is only 3 symmetries that allow you to do this trick to solve Gauss's law for the integrand E, the electric field. And that is, you either have to have a spherical charge distribution, or you have to have a cylindrical, infinitely long charge distribution, or you have to have a infinitely large flat plane charge distribution. If you don't have that, you're not going to be able to use the beautiful symmetries of the flux that appears on the left-hand side of Gauss's law to solve for the electric field. So that's the highbrow words / explanation behind all this. So what I need to do now is show you a couple of problems. I've already done 2 with your class. I'm going to do another one. In fact, one of them I'm getting ready to do. There's a delivery person here, baby. Sorry, I've just let my wife know, plus my dog's gonna go crazy otherwise. But anyways, there's a one that I did last time was for an infinite plane, but that was kind of rushed. So I'd like to do it again for you. And this time I'm going to go a couple steps further, because it turns out once you have the electric field for an infinite plane, you can basically figure out something about a capacitor, because capacitors are things we use in electronics, and you can sort of picture them as, let's say, 2 credit cards right beside each other. This credit card, say, maybe would be charged with a positive charge, and this credit card would be charged with the exact same charge but negative. That actually creates a magnetic field, electric field between them, and stores energy just like a battery does. Only, unlike a battery, you can drain it almost instantly, whereas a battery has to take some time to drain it and charge it. So let's start by sharing the screen again, but this time with my iPad. Feel free to stop me and ask questions. This stuff honestly should feel a little confusing initially, but what I'm trying to focus on is I want you guys to look at it and see what's common to each of these problems, because it's confusing by looking at the formula. It's confusing by listening to what we're doing. But if you just look at each problem, you see, oh my God, every time the left-hand side just becomes this. And if the left-hand side ever not becomes that, then you know something horribly wrong has happened. So what I'm going to do now is I am going to imagine an infinitely large sheet, flat sheet that's charged, and I'm going to use Gauss's law to calculate the electric field. Okay, so let's imagine our little sheet here. My sheet's going to be like this, say. And again, I'm estimating, but really what we're trying to suggest is that if I went out this way, I would never run to an end. And similarly, if I went out this way, I would never run to an end as either. So it's supposed to be infinitely large in every direction. What I'm going to do now is draw a nice little coordinate system. And since this thing's infinitely large, essentially all directions are perpendicular. Excuse me, all directions are I should say, all positions are in the center. Okay, so what I'm trying to do now is say this is going to be, say, my x-axis, this is going to be my y-axis, and this will be my z-axis, say. Now, this thing is going to have a charge per unit area. Remember, the rule was, I told you before, that dq is going to either equal lambda times dl, and that lambda can be a function of x or whatever. Since it's one dimensional, it can only be like a function of x or y or something. Or it's going to be sigma dA. That's for a surface charge. And of course, that sigma doesn't have to be a constant, but if they say it's uniformly charged, then it is. Or it can be rho dV, and that could also be a constant, but it could also be something like some constant times r, or some constant times r squared, or something like that. And that's how we can basically decide on the right hand side of Gauss's law, since Gauss's law says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. The right hand side of Gauss's law requires us to find the amount of charge enclosed. And sometimes, like when we're inside of a sphere like we were yesterday, we don't have access to all of the charge on the sphere. So I had to figure out what the charge enclosed was, which meant I either had to do one of those integrals or I had to find some kind of trick. And yesterday I showed you some kind of trick. Okay. So what we're seeing here is this plane has on it a positive charge per unit area, sigma, and the units of sigma, of course, would be coulombs per square meter or something like that. Now, because it's infinitely large, that means, like, yeah, you might have a positive charge right here, and you might have one right here, and that positive charge to the right might make you think over top of the left positive charge, you'll have a component this way. But if you look, there's another charge just like it right here. So that's going to cancel out. And I think by you thinking about it that way, and then considering the same thing with a spot in front of it and behind it, you'll see that there's no way for this infinitely large plane to have an electric field pointing any direction other than straight up above the plane and straight down below the plane. So my hypothesis is that the electric field is equal to E of Z K hat for Z greater than 0 and negative E of Z K hat for Z greater than 0. Okay. And what I'm saying by using that negative there and using the same symbol for both parts, E of Z, is by symmetry, we expect the electric field above the plane to be exactly equal in magnitude to the electric field below the plane. So that's why I didn't use an E1Z and an E2Z, for instance. And then the negative just dictates that it's going to point in the downward direction below the plane because it's positive charges, and you're going to try to get away from positive charges. And if the positive charges are above you, i.e. z is less than 0, oh, did I say it? I wrote it backwards, didn't I? Yep, I just realized that. I thought started to write it correctly. I remember doing it and I was like, oh no, you made a mistake. But no, I didn't. So yes, just make sure you correct this for z less than 0. Okay. So yeah, if you're at a point z less than 0, then the plane's above you and you see nothing but a buttload of positive charges. And obviously what we do to detect the direction of an electric field is we imagine which way a positive charge would be compelled to move. Clearly a positive charge is going to run away from that positive plane up above, and hence we have the electric field pointing down. So that's our hypothesis, and we're trying to calculate the electric field E equals question mark. Okay, that's the big question here. Now, what I'm going to do is make a Gaussian surface again. And in this case, I'm going to make a Gaussian surface. That's what we call a Gaussian pill bottle. And let's see if I can. Yeah, that's pretty good. Okay, so here's my Gaussian pill bottle. It comes down and intersects with the surface. And of course, we can't see through it, so that's why I had to draw it dotted back there. And we also can't see through the plane, so I have to draw it dotted back there as well. And you can see basically it's a Gaussian pill bottle. And check this out. I'm so old that I actually have a Gaussian pill bottle. So check this out. Ooh, see? So it's literally just a little cylinder, and you can imagine the plane going right through it. And of course, it has a flat circular top. And it's basically the shape of a soup can, except for the stupid thing for holding it on a keychain. Because, you know, if you're really cool, you can carry it on a keychain. But anyways, so that's what we mean when they keep saying this Gaussian pill bottle. I know when I was in college, I was like, what the crap's a pill bottle? Which I knew what pill bottles were, but I just never heard of one thing using such terminology. But anyways, that's what a Gaussian pill bottle is. And you actually technically don't have to make it cylindrical. In principle, you could have made it rectangular. It's just that cylindrical allows us so much more good stuff in terms of I can use coordinates that are nice and already created. So let's do stop share in a second. It's acting kind of weird when I try to share it again. Let's do share, do this, do this. There we go. So back to sharing my screen. So we're back to here. Now, since I made this hypothesis about the electric field that it may depend on Z, but it could only depend on Z. Notice it couldn't depend on X or Y just from the symmetry of the infinite plane. If it depended on X and Y, whatever tendency it had to be bigger because of one X is going to be canceled out by the diametrically opposed same X on the opposite side of the plane. So that's why it has to be only that. So what I'm going to do is I'm going to calculate the left-hand side. Remember, I use that terminology, left-hand side and right-hand side. And I do that because what we're solving for is a part of one side. And if I just started writing the left-hand side out and then worked it out to the right-hand side, that never ends up in me getting what I want. So if I take the time to work out the left-hand side, take the time to work out the right-hand side, and then set them equal, then you can sort of make sense of what I'm doing, namely solving for E. Okay, so we're going to do the left-hand side. So here's our solution. Left-hand side, closed integral E dot dA is going to equal, and I'm going to use some terminology, and we'll use some subscripts to make sense of what I'm doing. I'm going to integrate over each of the parts because it's got to be a closed surface. So I've got actually 3, you might even count it as 4 parts. I've got a lid, I've got a bottom, and then I got a top half of a soup label, and then I got a bottom half of a soup label. So you might even break that up. Now, what I'm doing with regards to the top is I'm imagining this little cylindrical coordinate differential area element, and I'm saying that little vector dA is just dA k hat. Okay, and I'll call that dA sub t for the top. Now, if you were actually understood cylindrical coordinates, or if you had coordinates, you know that dA is r d theta dr. You don't have to know that though, because the whole point of the symmetries of Gauss's law is so that you don't do that integral on the left-hand side. Okay, the way we use Gauss's law in solving for electric fields, the whole point of the left-hand side is that you don't do an integral. I mean, you're doing it, but you're avoiding it because the symmetry is so beautiful. Now, we also have over here on the soup label, there's going to, in fact, be, I'll draw it over here. There's going to be a height dz, and then there's going to be a width, which is r d theta. And that's what that little area is going to be. So you'd say r d theta dz would be the differential area element, but I'm going to call that dA soup label. And we don't care because we're just going to say dA, and I'm going to make a little trick and just call it n hat, where n hat is a normal vector, meaning normal to the surface of the soup label. What I really mean is technically n hat would be the, in polar coordinates, it would be the radial vector. So you could just write r hat there, or rho hat, whatever you wanted to do. Some books, when you're dealing with cylindrical coordinates, will use a different value for the distance from the origin to a point in the XY plane. They'll use a different value than r, because in spherical coordinates, it's always the distance from the origin to any point in space, whereas cylindrical coordinates, just the distance from the origin to a point in the XY plane. So I just called it n hat to avoid all that. You could call it r hat. You could call it rho hat if you're used to dealing with that. The main thing is, again, we just need a vector that we understand is perpendicular to the surface. And in this case, that's the n hat vector. And you can see that it points basically like the little arrow I drew. Now down here at the bottom, we also have that same little shape, if you will, but in this case, dA bottom, which I'll call dA sub b, is actually equal to negative dA k hat, because it has to point down. So what I end up getting is essentially 3/4 integrals. So I get the integral over the top of E of z k hat dotted with dA, whoa, dotted with dA k hat. That's my dA top, in other words. And notice on the top, they're both parallel. So that's sort of the whole point. Then we get plus. Now in this part, the way I could write it as two different integrals. I could write it for z greater than 0, and I'll have E pointing upward for all those. And then I do another one for E less than 0, and E would point negative in all those. But I think you're going to see it doesn't matter, because I'm going to write this integral right here, and I'm going to say plus or minus E of z k hat dotted with dA n hat. And the plus or minus just means, hey, when I go from z greater than 0, it's plus, but when I go to z less than 0, it's minus. But what do y'all think is going to happen with the k dot n hat, the k hat dot n hat? And this is for the soup label part.
It becomes scalar.
It does, but all dot products are scalars. But can you tell me what scalar it does become? Or can you tell me the angle between k hat and n hat?
Uh, 90 degrees.
90 degrees. And what's the cosine of 90?
0.
There you go. That's the key. Okay. And then we have plus the integral of negative E of Z K hat dotted with negative dA K hat, and that's for the bottom. Okay. So what we see here is the K hat dot N hat is equal to 0. So that term completely disappears. In this case, this just becomes E of Z, because we're doing a surface integral. That means we take the electric field and we have to evaluate it on the surface we're integrating. On the surface that we're integrating, that happens to be the very top of that pill bottle. And the very top of that pill bottle has a constant Z. So E of Z is a constant. It comes out in front of the integral. And we're left with dA K hat dot K hat. And I think you all know what K hat dot K hat is. Anyone? It's 1, exactly. And what do you think is going to happen down here for the bottom one? I've got negatives in there. Is that going to be okay? Notice I got a negative due to the dA and I got a negative due to the E of Z. I multiply a negative times a negative, I still get a positive, right? So if I call this surface area right here just A, then I think you can see the first integral is E of Z times A, and the second integral is E of Z times A as well. So I end up getting 2E of Z. Actually, I shouldn't write it this way. Should stick it back to red. I get 2E of Z times A for my left-hand side. Does that make sense to everyone? Thanks, Maya. So now here's the key. I've explained, how to make the sausage. Now you need to just forget about it. Okay. Later, when you get to vector calculus or you get in another class, advanced calculus, something like that, you might need to regurgitate this stuff and maybe you can pull out your notes and make sense of it. The main thing is I wanted you to know what's going on in that left-hand side, but the key is that you're always going to get either 0 or an electric field times an area. That area could be the surface area of a sphere. That area could be pi r squared. That area could be the surface area of the soup label portion of a soup can. But the main thing is always going to be electric field times that area, and you're never having to do the integral. So these extra steps I'm showing are wonderful. I want you to understand that's what's going on. And ideally, you could actually show that yourself, but don't worry too much if you don't understand it. That can come later. Okay. So now let's attack the right-hand side. So the right-hand side of Gauss's law says that the enclosed charge, and by enclosed, we mean the charge enclosed in the Gaussian closed surface that we made. So let me remind you that this red thing is a closed Gaussian surface. Okay, that's the key point to Gauss's law. You got to make a closed Gaussian surface. Then there's no ambiguity about which way the dA vectors point, because they always point from the inside towards the outside. The right-hand side is pretty wonderful. Remember, I'm telling you that the charge per unit area of the plate of the infinitely large plane is sigma. Can someone now guess what the total charge within that little part right here, can anybody tell me how much charge would be inside of there? Can anybody tell me what units the thing has that you have to multiply by sigma to get charge? About that. So sigma is the charge per unit area, we said. Can you tell me what the units of the thing I have to multiply by sigma to get the actual charge would be?
Is it the area?
It's the area, exactly. Because it's charge per unit area. So if you multiply charge per unit area times area, you just get charge. Have we made any conclusions about what that area is on any part of the drawing or the other side of the equation or anything? It's in blue if that helps you on the picture, and it's in red on the left-hand side of the equation.
Is it the final answer, the 2e of ZA?
Yeah, it's the A that's in the 2EA. So the right-hand side just becomes, let me put it back on red, just becomes sigma times A over epsilon naught. Because as I drew right here, that area of the top of the soup can, and it is a soup can or pill bottle or whatever, so that's the same area of the intersection with the inside of the soup can and the infinite plane. So now I can set left-hand side equal to right-hand side, and I get 2e of z. Don't forget that's a function of z. And sometimes you might not ever want to write it, in fact, once you get to this point, but I always put it there just to make sure no one lost what I did. And then the right-hand side was sigma A over epsilon naught. So we can conclude, now I'm going back to my hypothesis here, which actually technically I didn't put a vector symbol on, but I should have, so I did now. So my hypothesis is that the electric field is a piecewise function, and that piecewise function is going to be, in fact, notice the A's cancel out, and I'm going to get sigma over 2 epsilon naught k hat for z greater than 0, and I'm going to get negative sigma over 2 epsilon naught k hat for z less than 0. That's it in a nutshell. That is the solution for the electric field. And in fact, that's something that's kind of interesting. Let me draw, this is really pedantic to some extent, but still, I'm going to draw the electric field magnitude as a function of position. So here is, in fact, our z-axis. And here is, in fact, our electric field axis. And this will be sigma over 2 epsilon naught. And this will be the electric field there. And down here will be negative sigma over 2 epsilon naught. And that will be my electric field. So unlike the one I did yesterday, remember the one I did yesterday was a continuously distributed or evenly distributed charge throughout a non-conducting sphere. and it was basically linear, and then it right where the linear ended, it matched the dot of the 1/r² part, and it fell off. It didn't have a discontinuity. This one clearly has a discontinuity, and in fact, you could say the discontinuity is from here to here. That's a discontinuity in the perpendicular component of E. And that discontinuity is in fact sigma over epsilon naught, which is a fundamental idea within Maxwell's equations anyways. It turns out that the electric field perpendicular to a surface is always continuous unless there is a surface charge, in which case it's exactly discontinuous by an amount sigma over epsilon naught, and that's what this shows. Notice you'd have to go half of sigma over epsilon naught up, but you'd also have to go half of sigma epsilon naught down, so the sum of those two give you sigma over epsilon naught. Okay. That's called, boundary conditions for Maxwell's equations, talking about the perpendicular component at an interface. And you also talk about the parallel component of an interface, and then we get to magnetic fields, you'll do the same thing. So now that we have that, I want to examine something else kind of neat. Let's say we have this plate right here, and that has a charge that is positive. And let's say we have this plate right here, and they're actually going to be way closer to each other relative to their size. That's going to be negative charge. And I'm going to say this is actually in 3 dimensions. So first off, I want to say my red plate goes like this. And my blue plate, of course, goes off the same way. That's actually what something we call a capacitor. It's a type of capacitor. There's other types, of course, but it is a capacitor. So if we look at it from the side, it looks a lot simpler. And that's what I drew first, was just the side view. So I draw that here again in side view just to make it a little easier. Okay. Now, what I want you to tell me is, according to the result we just got, what is the electric field due to the blue one right here where that dot is? So I just drew a black dot in between the red and the blue. So which direction is the electric field due to the blue plate pointing? At that spot where the black dot is. To the right or to the left?
To the right.
Exactly. Now, what about the electric field due to the red plate? Remember, the red plate's negative, and the electric field direction is the direction in which a positive charge would want to go. So we're pretending the blue plate's not there at all, and I stick a positive charge at that black dot. Which way does the red electric field make that positive charge want to go?
To the right.
To the right as well. And do you see that since they're both the same charge and they're both the same size, clearly the charge per unit area is the same, so they actually have the same magnetic, or excuse me, the same electric field strength, wouldn't they? So what happens is, inside, in between these plates, the electric field strength is not sigma over 2 epsilon naught, but just sigma over epsilon naught, because it gets a sigma over 2 epsilon naught from the blue one, and then it gets a sigma over 2 epsilon naught from the red one, and they're parallel, so they actually contribute to each other. Now, what about at this black dot, or let's say at this black X here? Which way does the electric field due to the blue one point?
It's unaffected by the blue.
Exactly. So it's not affected. Yeah, it shouldn't be affected by the red one. We're just, in fact, we're trying to think as if the red one's not even there. So which direction did the blue electric field seem to point at that X?
To the right.
To the right. Very good. And what about the red one?
Left.
Exactly. And remember, they only depend on the charge per unit area, at least as long as you're close to them. So in this case, the electric field over here is 0. What about at this side over here? What do you think is going to happen where that little star is? Which way does the blue field act? The blue field points to the left, right? Are correct. And the red field will point to the right. So again, on this side, we get an electric field equal to 0. So that's what happens when you put two parallel plates next to each other. If they happen to be roughly or pretty much the same size and have the same total charge, then their charge per unit area is the same. And in fact, you can get them really, really close. But what ultimately happens if you get them too close, the electric field between them can get strong enough to force air to become a conductor. That happens at about 3 million volts per meter. So once you get about a meter apart, if you've got 3 million volts, I think that's the number off the top of my head, then lightning will literally strike from either the blue one to the red one, which is the more normal scenario where you actually lose some. The normal scenario is normally use some move some electrons, so the electrons would jump off the red and run to the blue. If that's only a centimeter apart, that and I'm right about 3 million volts per 3 million volts per meter, then when it's a centimeter, it only need to be 300,000. So you can figure like that, but that's really what happens. And you might imagine that there's a good reason for them to be close together. It turns out the capacitance, the thing that matters about this thing, is something called the capacitance. It's the charge per unit voltage. And that capacitance is gotten larger by making the distance between the plates smaller. And it's also gotten larger by making the area larger. So the ideal scenario would be like 2 football fields within, a piece of paper between them. That would be really ideal for a really huge capacitor. So we'll get to capacitors later, but we now know that. So I need to know another symmetry. We've now done 2. We've done spherical symmetry, and now we've done cylindrical symmetry. Well, actually, we sort of did cylindrical symmetry by using a cylindrical pill bottle, but we actually did infinitely large plane symmetry. So let's imagine now, instead of doing infinite plane, let's go back and do that very first nasty integral problem we did on when we got into chapter 21, section 7. So we're going to do that. So the question is, use Gauss's law to derive the E field near and actually I shouldn't write it that way, and infinitely long uniformly, let's make that a charged wire. So remember that nasty integral we did? Well, we don't have to do that with Gauss's law. So let me start off by drawing a nice little coordinate system again, just like we did before. So there's my fancy y-axis. There's my fancy x-axis. And let's go ahead and I'm going to draw my wire as if it's red. And in fact, this wire goes on for infinity that way and that way. Okay. Now, what I'm going to do is I'm going to imagine a small part of it. So let's say this part right here, from here to here, has a length L. And I know that looking at this charge distribution, lambda equals dq over dl equals a constant is what we have here. And that's because it is uniformly charged, right? So I'm going to bite off a length big L, and I'm going to think about that big L. What we know from our past working with Coulomb's law, if I have a string of charges along the y-axis, then if I happen to be on the x-axis, the electric field will point in the positive x direction if I'm in the positive x-axis. But if I'm on the negative x-axis, it'll point in the negative x direction. So let me show that with a different color just to give you all an idea. So if I'm right here on this axis, the electric field will point that way. Now let me put back black so I can go ahead and say this will be our z-axis coming out of here. Okay, this will be our z-axis. And if I now pick a point in space, say right here on the z-axis, then the electric field would point radially outward. If I pick a point back here, the electric field will point radially inward. If I pick a point over here, it'll point that way. Do y'all see that that's the case? The electric field's always going to point away from the y-axis. Does that make sense? Even this point right here is going to make a electric field pointing that way. So if you imagine a shape that would always have those lines perpendicular to its surface, I think you can come up with the Gaussian shape that we would need. Can anybody think of a Gaussian surface we would need to enclose this wire with so that the electric field is going to be exactly parallel to the dA vectors? Anybody? Don't worry if you can't. It's pretty much, I mean, it's a tough thing, but I've never had anybody answer it correctly, but it's worth a try every time.
What was the question?
So we're trying to come up with a Gaussian surface, and the rule for when we're using Gauss's law to solve for the electric field is that we want the Gaussian surface to be defined such that the dA vector is everywhere parallel to the electric field, or it's completely perpendicular to the electric field. So can you tell me one surface that would be everywhere parallel to the electric field? Remember, the dA vectors are actually going to be perpendicular to the surface, but we're saying that the dA vectors and the E are going to be parallel. Anyone? Okay. Well, how about this? What if I choose a Gaussian surface like this. You all see that everywhere the electric field is will have a dA vector perpendicular to the little soup label, which actually is parallel to the dA vectors. And on the top and bottom, the electric field will be perpendicular to the dA vector, so you get 0 there. So that's our Gaussian surface. And it's going to be a cylinder, obviously, of radius r and length L. Okay. So up here, in fact, we'll have a little differential area element, dA top, which is just going to be dA k hat. Down here, we'll have a differential area element, dA bottom, which is going to be negative dA k hat. And then if you think about, let's say this little spot right here, you're going to have a differential area element, dA soup label is equal to dA. And remember, before we used the n hat, I'll go ahead and use a rho hat this time just to mix it up a little bit. But basically what we're saying is this rho is just like a radial vector. In other words, it's a radial vector that doesn't realize we have a z, or excuse me, doesn't realize we have a z dimension. It's just in the x, or excuse me, doesn't realize we have a y dimension. It's just in the xz plane. So that's what I mean by that. Okay. And you see that it's actually, in fact, parallel to the electric field. And that brings us to our hypothesis and, of course, our solution. So first off, we have a hypothesis. The hypothesis is that the electric field is equal to E of R pointing in that crazy rho hat direction. Again, I've got my axes a little skewed. Technically, I would want to make that thing coming out of the board the x-axis, that thing going to the right, the y-axis, and that thing going up the z-axis. Then I'd be in real territory where I'm actually using the cylindrical coordinate systems. It doesn't matter. The main thing is that you have some understanding of what the directions are. In other words, the directions and the direction vectors that I use. So the right-hand side of Gauss's law, you guys might want to try to think ahead and see if you know what this is already, because at this point you should be able to just write it down, and that's what you're going to do on a test. You're not going to show me all these gory details that I'm showing you, but the closed integral of E dot dA is what we got to compute. And that first off is going to give us an integral over the top, which is going to be E of R rho hat dotted with dA k hat. And then we're going to get a plus integral over the soup label portion, which would be E of R rho hat dotted with dA rho hat. And then we're going to get an integral over the bottom of E of R rho hat dotted with negative dA k hat. Anybody want to tell me what rho hat dot k hat is?
Is it 0 again?
Yes. So we pull the dA and the E of R out in front and we get rho hat dot K hat, but rho hat dot K hat is just 0. And same thing happens here. This part becomes the integral of E of R dA rho hat. There's a negative out here dotted with K hat, but this part right here is again 0. So this whole thing becomes 0. So that's what I mean. The left-hand side is always going to become an electric field times an area or 0. So all we have left on the left-hand side, or excuse me, I called that right-hand side. What was I thinking? Let me fix that real quick. Everybody, that was not the right-hand side. Y'all probably were all laughing at me internally for being such a goober, but anyways, it is the left-hand side. So the left-hand side will always become E times A, or like we just saw, 2 times E times A, or 0. If it doesn't, you've done something wrong, and you shouldn't. You should be stopping your problem right then and going back and reapplying Gauss's law, or it's a problem that you can't do Gauss's law with, at least not for that purpose. So in this case, all we get for this soup label integral is that the electric field will be multiplied by the area of the soup label. So I'm going to write E of R. And given that the can is L units tall and the radius of the can is R, can y'all tell me the formula for the area of the soup label? Imagine maybe taking the soup can, if this is obviously not cylindrical, but imagine cutting a slice straight down the side of the soup can, and now your soup label, if it's not stuck too well, it'll just come off and be a rectangle. Can y'all tell me how to calculate that rectangular area? What's the height going to be? What's the width or the length of that thing going to be?
Length times width.
Yeah, length times width. Can you tell me what the length is, since it used to be wrapped around a soup can?
The circumference.
Exactly. So the answer is 2 pi r times L, right? All right. Now, if I tell you, like I did here, that the charge per unit area, or excuse me, charge per unit length is lambda, can you guys work out the right-hand side for me? So here's the right-hand side. And according to Gauss's law, the right-hand side is the total charge enclosed by the Gaussian surface divided by epsilon naught. Can anybody tell me what the charge enclosed is going to be inside that little blue Gaussian surface? All right, tell me this. If I want to use lambda to find the total charge, what units must the thing have that I multiply by lambda to get the charge?
L.
Very good. Lambda L. He went ahead and answered the whole question. So that's good too. Okay. So yeah, that's the right-hand side of Gauss's law. Now I just say left-hand side equals right-hand side and pretend that strokey thing that happened to me and where I wrote the wrong side, that never happened. So we're not going to write E of R times 2 pi R L is equal to lambda L over epsilon naught. And are we just amazing or what? Because this is exactly the result we got when I did it that horrible integral way, right? So ultimately, going back to my hypothesis, I now know that the electric field is in fact E equals lambda over 2 pi epsilon naught r in what I called the rho hat direction. And that's it. Notice that is exactly the same result as we did when we got when we did it with that nasty integral. Isn't that kind of cool?
I have a question.
Yes.
How do you determine whether you use lambda or sigma or rho?
So if you look at the different scenarios we did, you can tell from the geometry of the thing that has the charge. So for instance, the first problem we did last time with Gauss's law was a sphere. It was a non-conducting sphere and the charge was uniformly distributed throughout. Since it's a sphere, we already know it's a three-dimensional object. If I'd said a circular disc, that wouldn't have been a three-dimensional object. That would have been a two-dimensional disc. That would have been a two-dimensional object. But since I had a three-dimensional disc, I automatically have to think rho. So, or excuse me, since I have three-dimensional, not disc, I'll automatically have to think rho. Okay. Now, when I did an infinite plane, that was innately two-dimensional. So I had to think sigma, because that's charge per unit area. And then this thing, believe it or not, you're pretending like it's infinitesimally wide left and right, and it's infinitesimally wide forward and backwards. And then it has some length in that third dimension. So it's literally a one-dimensional object. So that makes you think lambda. Does that help you a little bit?
Yeah.
And that is the question that students almost have every semester. So you're right on par. So don't feel bad if you feel confused about that. That was perfectly normal. All right. Now, there's a lot of cool stuff about Gauss's law. You can use it to show, for instance, that whenever you have a conductor, meaning a metal, and you put charge on it, all the charge will actually force itself to get on the outer edges of the metal. And you can use Gauss's law to help you decide that. You can also use Gauss's law to help you decide things like, let me show you this one. This is a good example. So here's another example we're doing related to Gauss's law, but not for solving the electric field. So let's say we have a little point charge right here, positive Q. It's inside of a cavity inside a blob of metal like this. Okay. So, and this is a conductor. So first off, I'd say, what is the charge on the walls of the hole? So there's a little cavity in there. This is a three-dimensional object. So we're actually seeing through the walls of the conductor to see that little hole that the Q is in. But what we know about conductors is that unless you have a battery connected to it so that it could drive current through it, there's basically no charges inside the conductor. Okay. It can't be, because the nature of a conductor is that conductors allow charges to move wherever they want to, and they're going to obviously move as far away as they can, which will be on the outside edges. So if I take a little Gaussian surface and put it just barely inside the conductor, make it a sphere, that could be a spherical cavity. It doesn't have to be a spherical cavity, in which case I just make a Gaussian surface that's exactly the same shape as that cavity. But in a sphere, it's a little easier to see. But notice, because it's in there, we know that the closed integral of E dot dA is equal to Q enclosed over epsilon naught. We know that the electric field inside the conductor has got to equal 0, because all the charges have to run away And in fact, we will find later that the entire surface of a conductor is a equal potential. So the electric field really has to be zero in there. So since the left-hand side zero, what that means is the total charge inside that Gaussian surface is zero. So that means there evidently has to be a charge of negative Q on the inside wall of that cavity. Now, if that conductor was initially not charged and that, charge Q was, let's say, transported in there in like a Star Trek fashion, then instantly what would happen is, because the charges left the conductor to go into the inside surface of that cavity, that would leave a net positive charge on the outside on the conductor. So the conductor would now have a charge of positive Q oriented all around the outside edge of the conductor. So that's sort of some neat little stuff you could do with Gauss's law, just making readings. So one of the big things you have to learn is that in the situations we're studying, which is static electricity and magnetism, basically, we haven't hooked up sources of current and stuff like that. Basically, the electric field inside of a voltage inside of a conductor has to be zero. And that makes, in fact, the entire conductor be a equal potential surface, which is the next chapter we're going to learn about voltage. And equal potential means the voltage is the same all over the entire conductor. So that's another thing you can learn. There's another neat little problem I've seen before. Let me give you this one. This is kind of cool. So let's say we have a charge. I'm going to try to use the nice drawing features. Let's say that's a charge Q. And let's say that charge Q is at the corner of a cube. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Oops. Let's undo that last one. Okay, something like that. So, whoa, where'd that extra circle come from? I didn't see that come into play. Ah. Oh, that was stupid me. Where'd that extra Q come, that extra circle come from? And what's the little line on it? Yeah, Mr. Younger, that's a Q. Okay. Let's put our little Q down here. Now, this is a perfect cube, say. So I'm going to say this goes straight down to here. This goes straight back to here. This goes straight back to here. And what I would like to know is what is the flux through that face? And evidently I've turned into Yoda because I'm saying flux through the space equals what? I don't know where that came from, but anyways. This was kind of tricky. What we know from Gauss's law is that if you fully enclose a charge within a closed surface, the net flux through the surface is that charge divided by epsilon naught. And if the surface that encloses the charge has certain symmetries, then you can make arguments like, well, the back has to have exactly the same amount of flux as the front, or the right has the same amount of flux as the left. stuff like that. So that's a big hint I can give you on doing this. Anybody think they might have something? And I'm really bad with this thing. I'm gonna try to erase that real quick. Get rid of that thing. I don't think I can. Nope, I can't. I hate how that's not quite right. So anybody think you can look at that and figure out something? That looks moderately better. Anyone? All right. How about if I do this? Keep on thinking about it, but how about if I do this? Anybody have an idea now? So now that we have this, and actually I can do it a little better since I didn't realize there was a piece of the page sticking out like that. But anyways, it should go like this. Okay. Now we see by drawing this drawing, I actually have the Q entirely inside of a cube, another cube. And in fact, we know that the total flux through that has got to be Q over epsilon naught. Now we also know, let's do a different color than this. Let's do this dark blue. This face right here, from the symmetry of it, is just like the left face, which is just like the front face and the back face, which is just like the top face and the bottom face. So this plate is responsible for 1/6 of the flux. Does that make sense?
Yeah.
So what do you think the flux going through the little blue box, the blue line one is?
(136) or 1/24.
1/24. There you go. Good job. So the flux through that little part is Q over 24 epsilon naught. Excellent. Isn't that a neat little problem? Man, I must have spent hours trying to figure that out. And then when I realized it, I was like, God, that was so stupid. How did I not figure that out? But be advised, that's what we do. And I think engineers do it too. We basically consider any problem we haven't solved or that's hard for us. It's impossible. It's insoluble. It's undoable. And then once we do it, no matter how hard it is, even if it took us 3 days to calculate it, then it's trivial. So there's really no in between. There's infinitely hard and there's trivial. And the only difference is whether we've done them or not. But anyway, so that's some more stuff about Gauss's law. I'm going to do my best to try to post several Gauss's law videos between now and Monday. And of course, we meet on Tuesdays and Thursdays, but I might even be able to do more by Tuesday. But anyways, it's now 6:38. That's 2 minutes till class is over. You guys are completely welcome to cruise. Please notice those of you that came in late. I told at the beginning of this video, I told everybody that I had actually adjusted the due dates on the homeworks for chapters 21 and 22. And I got rid of 2 of the extra, physics primer things, and I changed those dates as well. So make sure you get your physics primer and your intro to mastering physics done. Make sure you get your chapter 21 done, and make sure you get your chapter 22 done. We've now done way plenty for you to do chapter 22, and I've given you more time to do it. So go ahead and get that done. I think I gave you till Tuesday, but it might have been till Wednesday to get chapter 22 and 21 done. But check on my lab and mastering for that. And you guys have a great, safe weekend. Let me know if you need anything, if you have any questions, but you are free to go, and I'll wait for the last person out in case anybody has any questions. Hey, I'm the only one in here.